Hello, my name is Mohamed Main and I am a PhD student. In this video, I will present my research on the aerodynamic drag. The title of this presentation is Numerical Study of a 2D Cylinder by Durance Method in the Supercritical Regime. In this presentation, we will see firstly an introduction, secondly mathematical model, thirdly numerical simulation, then results and discussions, and finally a conclusion. As an introduction, one of the classic problems of fluid is the flow around the circular cylinder. Modeling the flow around the unformed bodies is essential work in many engineering applications. It aims to determine the loads and the mechanical response of a structure stressed to a fluid. Many research has been done in this domain. Schmitz, Aschenbach, Jones, James, and Steve carried out experimental works on the flow around a cylinder for Reynolds number greater than 10 power 6. Many numerical research has been done on numerical simulation, as Catalano, Singh, and Metal, Ong, Pang evaluate the ability of the standard K epsilon and K omega models to predict the flow around a cylinder in the supercritical regime, that means in the high Reynolds number. This presentation aims to study the ability of Durance and study Reynolds average Navier-Stokes model using the two-equation system K omega SST to predict the flow around a 1 meter diameter cylinder in the high Reynolds number. Mathematical model. The governing equations. Since the flow was considered incompressible, that means the energy balance does not intervene. The flow is governed by the mass balance equation and in addition by the momentum balance equations, where UE is the free stream velocity in I direction, ρ the specific density, P the pressure, and nu the kinematic viscosity of the fluid. For the Durance turbulence model, that means unsteady Reynolds average Navier-Stokes, we use the Reynolds average. The Reynolds average was applied to the two previous continuity and Navier-Stokes equations by decomposing the variable u and p, the velocity and the pressure. The equations become for the continuity and for the momentum equations. For closing the equations, we use the turbulence model K omega SST. The K omega SST shear stress transport model developed by Manter combines the precision of the K omega model in the near wall and the K epsilon model in the far field region. Such an approach was made by transforming the K epsilon into a formulation K omega with the addition of a blending function between the two regions. The turbulence kinetic energy and specific dissipation rate are determined as follows, where u0 is the mean velocity and I is the turbulence intensity. Numerical simulation. Firstly, we will see the boundary conditions. The geometric shape of the computational domain shown in figure 1 is a rectangle whose the cylinder is 20d away from the inlet wall and 40d from the outlet wall along the x-axis. The cylinder is located along the y-axis of 20d of the two upper and lower walls of the domain, where d is the diameter of the cylinder. For the input flow, ux is equal to u0, the free stream velocity, uy is equal to 0, the k is calculated, and omega is also calculated. For the output flow, all the parameters are free. For the lower and upper walls of the domain, uy was 0, while the other parameters are free. For the boundary layer of the cylinder, ux was equal to free stream velocity, uy is equal to 0. Mesh and independence test. The mission is carried out on ICM-CFD and exported to Fluent. Figure 2 represents the boundary layer of the cylinder which is refined for each type of mesh. The near wall refinement is carried out by calculating the height of the first cell. Each mesh is simulated for 3 different time steps, calculated from the Strohan number. Also, each simulation is launched for 500 time steps, and each time steps contain 20 iterations. Figure 3 presents the distribution of the coefficient Y plus on the boundary layer of the cylinder for the 3 types of meshes, with delta T is equal to 0.00251. It is quite obvious that Y plus is less than 1 along the contour of the cylinder, which shows that the condition of mesh in the boundary layer is well respected. 3 important parameters are evaluated. The mean drag coefficient and the root mean square length are calculated by the following equations. The Strohan number represents the ratio of the advection time and the characteristic time of unstationarity. It is calculated by the following equation. Results and discussions. After a set of numerical calculations, the result obtained in Table 1 show an overall variation of the drag coefficient between 0.364 and 0.405. The root mean square length coefficient varied between 0.044 and 0.115, while the Strohan number is between 0.214 and 0.315. This value shows that the time steps has an effect on the variation on the various coefficient. By comparing the 3 types of mesh, coarse, medium, and refined, for a type step delta T equal to 0.00251, one notes an independence of the results compared to the mesh for coefficient drag and Strohan number, since the rate of variation of the drag coefficient average in less than 5%, and the rate for the Strohan number is less than 8.5%, show it in the table 2. A strong variation of the left coefficient in the root mean square is observed, approximately 25%. Figure 4 illustrates the distribution of the input speed on the x-axis. It can be seen that the inlet velocity remains uniform on the axis up to a distance of 1.5 meter in front of the contour of the cylinder and drops sharply to 0 meter per second in contact with the wall. Then the speed increases behind the cylinder to reach 70 meter per second over a distance of 5.5 meter away from the wall. In this zone, there is a strong turbulence due to the separation of the boundary layer in the wake zone. Figure 5 plots the distribution of the pressure on the surface of the cylinder that is 3500 Pascal in contact with the front surface of the cylinder. Afterward, the pressure decreases sharply in the two lower and upper contours to reach a maximum value of depression equal to minus 8500 Pascal, which is due to a sharp increase of the speed in this area. Then the pressure increases to a value of minus 2000 Pascal in the bake surface. The result obtained from the average mesh for a type step of 0.00251 are compared with those obtained in the literature. Generally, current predictions are within the range of experimental data and within reasonable limits, consistent with publishing numerical results. It can be seen that the drag coefficient has a maximum variation of less than 15% compared to the result of the authors Catalano, Ang, and Pang for Durance turbulence model according to the two types of equation K epsilon and K omega. However, the results show that the Lees model varied by 26% and slightly more compared to the experimental data. For the other two parameters, the result showed that the Strohan number varied slightly compared to the root mean square left coefficient. The maximum of variation observed at the level of the coefficients Strohan and left coefficient are respectively 25% and 43% compared to the data in the literature. Figure 6 shows the variation of the drag coefficient as a function of the Reynolds number. In the supercritical regime, the drag coefficient decreases slightly as the Reynolds number increases. There are small fluctuations between the current results and diurnes reported by Catalano. Overall, it is observed that for the very high Reynolds number, the drag coefficient varied between 0.2 and 0.7. This strong variation is due to the turbulent region. Figure 7 shows the distribution of the pressure coefficient on the surface of the cylinder according to the angle. For a Reynolds number of 5.2 10 power 6, the pressure coefficient obtained is compared to the numerical results of three authors, Ong, Catalano, Seng, and the experimental study of Warshauer and Lin at a Reynolds number of 1.2 10 power 6. It is observed that the present study offers a better correlation with Diurnes model of Catalano and Ong. A moderate variation from the separation zone is observed between the different results. This can be justified by the difficulty of modeling the turbulence in areas which have a strong variation in the pressure gradient. Figure 8 shows the velocity contour around the cylinder at time of 1.255 seconds for a Reynolds number of 5.2 10 power 6. It seems that the current model is able to produce the periodic vortices qualitatively according to the 6 turbulence regime described by Linhart in figure 9. As a conclusion, in this presentation, the flow around a 2D circular cylinder has been studied for very high Reynolds number using Diurnes 2D turbulence model in conjunction with the K-omega SST model. The mesh in the boundary layer is calculated from a y plus equal to 1. An independence test was carried out on three types of mesh, coarse, medium, and refined, for three types of time steps. Several parameters were evaluated: the drag coefficient, the lift coefficient of root mean square, the pressure coefficient, and the Strouhal number. The preliminary results are promising in that they currently predict the drag coefficient, the pressure coefficient, and the Strouhal number. The turbulence model gives satisfactory qualitative agreements with the data of numerical and experimental results published in supercritical flow regimes. For this study, it is to be cited that the Diurnes K-omega SST turbulence model can predict the turbulence reliably in the supercritical regime, which allows using it as an engineering tool for the evaluation of design work. For the references used in this presentation, and thank you for your attention.